Good afternoon, everyone. My name is Andrew Flattabo. I'm a VR developer at NASA Johnson Space Center in Houston, Texas. Before I begin, I just want to say thank you to Epic for inviting us here today. It's an honor to be here talking about three things I love, which is VR, Unreal Engine, and NASA. So we have a double feature for you today. I'm going to start off talking about how we're using VR for design, and then my colleague Lee will join to talk about using XR for training. It'll be interesting to see our different philosophies towards using VR and Unreal Engine. I'll start off talking about my team, who we are, why we use VR, and then I'll guide you through one of our bigger projects. There's not too much technical depth, but there are some tips for the developers in the audience. So there are a few different VR teams at NASA. My team is part of the Center for Design and Space Architecture, the CDSA. We're part of the Human Health and Performance Directorate, which is the primary organization focused on humans living and working in space. Our mission is to lead the global spaceflight community in protecting astronaut health and ensuring human mission performance. The CDSA offers end-to-end development and concept engineering services to help our customers envision space vehicles based on future market needs and mature their designs towards fabrication. Our capabilities include mock-ups from part task models to full-scale functional prototypes. And we have a design methodology that promotes intuitive interactions, ergonomic efficiency, and real astronaut behavior. So virtual reality offers a powerful set of tools for spacecraft design. It starts off with immersive spatial understanding, which helps teams assess layout, scale, and human factors with high fidelity. VR facilitates clear technical communication by providing a shared visual context for cross-disciplinary and international collaboration. And because we can iterate quickly in VR, it speeds up the development process, reducing our reliance on physical mock-ups, saving both time and money. With VR, we can do a much deeper evaluation of our designs, which means we can make better decisions from start to finish and catch potential problems early before they become bigger issues. When it comes to mission planning, VR makes the process feel more real, helping teams work through scenarios in a way that leads to safer, more efficient operations. Another major benefit of VR is it gives everyone involved in the project a clear, more intuitive understanding of what they're building. We offer hands-on demos to a wide range of teams at the agencies. We have engineers, designers, project managers, interns, and astronauts in, so they can fully experience the work in a tangible way. If a picture is worth 1,000 words, I think VR might be worth a million. These immersive sessions often spark insightful conversations that lead to better design decisions. So human-centered design guides the work my team does, directly shaping the functionality of the projects. By analyzing movement, task performance, and spatial perception in VR, we create spacecraft layouts that enhance crew comfort, safety, and efficiency, which are all crucial for long-duration missions. Task analysis helps align spacecraft systems with human capabilities, leading to simpler interfaces, better layouts, and reduced cognitive load for a safer, more intuitive environment for the crew. So our team is basically an in-house game studio. A program might come to us with a need for VR, or you might suggest VR for a specific task if we're already working on them with a program. So we budget time and resources, and we build it. Projects can take anywhere from a few weeks to over 6 months to build, and we constantly juggle multiple projects at once. We're a small team. There's only a few of us. We use the VR expansion plugin as a C++ base because it provides a solid foundation for multiplayer and replication. We build out our pawn and functionality off of those base classes and keep it in our own plugin system that we use as a starting point for all of our projects. I dig into C++ to create specific things, but we're so focused on quick design and fast iteration that, and blueprints handle majority of what we need at this point. We also make use of the DLSS plugin, and that is a necessary component to keep our projects performant in VR with the sheer amount of meshes we use. So just really quickly about hardware, since it's always asked. We use 4 Oculus Quest 3s for multiplayer. So this diagram is half of our setup. We can have 2 Oculus Quest 3s attached to one unified access point, which is then connected by Ethernet to a router, and then by Ethernet to 2 desktop PCs. We use Bonobo head straps with swappable battery packs, so we don't have to worry about running out of power during long demos. And we use 4090s with i9s and 64 gigabytes of RAM. So I'm going to introduce one of our bigger projects and go into some depth. Artemis is NASA's program to send humans back to the moon and eventually on to Mars. The Lunar Gateway has been in the works since 2017 as a modular space station that will orbit the moon and serve as a staging point for human and robotic missions to the surface. It's not meant to be permanently crewed like the International Space Station, but astronauts will visit it during Artemis missions. It's an international effort. Modules and craft are being designed and assembled by multiple companies and space agencies across the world. We built a complete simulation of the fully assembled gateway, showcasing its modular design and how it evolves across missions. Each module is built as a standalone blueprint, and any interactable actors, such as stowage or equipment, are set up inside as child actors. The structure allows us to move entire modules with the push of a button and lets us test different configurations on the fly. So obviously with microgravity movements, we need to simulate microgravity movement to some extent. Or with microgravity environments, we need to simulate microgravity movement. So with so many people coming in with varying degrees of experience with VR, we had to create something that was somewhat beginner-friendly. The user sits in a swivel chair with their feet up, so that gives them at least 360-degree freedom of movement. And so moving inside microgravity environment is called translating. And to do this in our projects, the user will stick out their hand on a surface, use the grab button to grab the surface, and then pull or push themselves and let go. It's physics-based, so they'll continue flying in that direction and bounce off walls till they steady themselves by grabbing another surface. So you can imagine how that might make some people sick. So we also have a fly button, which enables them to push the thumbstick and move in any direction they want. And when they let go, they'll come to a complete stop. So we found giving them the option to rotate smoothly on a non-90-degree axis was a recipe for motion sickness. So as a general rule, we just don't let players rotate themselves besides physically moving in a circle on the chair. We can press keys that rotate them along a 90-degree axis if needed. This is important since there's no definitive up in space, and we need to test different orientations of the spacecraft. We also have the ability to add tractors to the feet and the elbows if we're doing a more involved volumetric analysis. This also has the added benefit of allowing them to use their feet to anchor themselves in place, much like using the hand to grab the surface. You can use your feet to grab the surface. This is something that real astronauts do more often in zero gravity, because by using their feet to steady themselves, it keeps their hands free for whatever task they're working on. So we continue to design and refine a wide range of meaningful interactions between the user and spacecraft environment. These interactions support realistic task performance and design evaluation. Examples include managing and relocating stowage elements, relocating handle positions for optimal reach, operating hatches, including opening, closing, and locking mechanisms, capturing imagery using a virtual Nikon camera, and deploying and interacting with scientific payloads. So Nanite has been godsend for us in terms of improving our efficiency and accuracy of models. The increased accuracy in geometry from being able to use models that are pretty much the same fidelity as the original CAD gives us much better feedback. So the way it works is that we'll get the CAD files for each module. We'll use Rhino to export manageable blocks. We'll bring them into Blender, where we merge faces and assign materials. And then we'll export those as FBX and bring them into Unreal Engine as Nanite. Each module has around 20 to 50 meshes. The old way before Nanite, we would fake geometry by baking it into the material. And doing it the old way would take 3 people a couple weeks to fully import all the meshes for one module. The new way takes 1 person a couple of days. Materials are usually created with the Substance plugin using the triplanar projection option. So at the top of the slides is the stat for the Gateway Space Station with all the modules visible. We actually got a CAD drop a couple weeks ago, so we're over 150 million now. In station, we've had some problems with nanite meshes popping in and out like bad LODs. Grouping faces to a smaller area during Rhino export usually helps. But we also typically use these two settings. If I'm having issue with a particular mesh, I will update the value of the minimum residency incrementally until it behaves properly. Also, adjusting the fallback relative error helps to fix issues such as curved objects looking faceted. Setting it to 0 will help with a particularly deformed looking mesh. Collision is an issue as well, since the user has to grab any surface to be able to translate. So if we use complex collisions for everything, if we had a physics objects like some stowage bouncing around in there, it would just cause major performance issues. So we'll use the in-editor collision generator when it makes sense, when it's simple, but we'll often just bring the mesh back into Blender and make sort of a quick outline mesh and then use it as a custom complex collision. So we use Lumen and IES profiles to accurately depict lighting while still being performant in VR. An IES profile stands for Illuminating Engineering Society profile and is a data file format used to accurately describe the light distribution characteristics of a specific light source. Realistic lighting in VR is important for spacecraft design. It creates an immersive environment that helps visualize how the spacecraft will function under real-world conditions, including emergencies or varying light levels in space. Prior to 5.5, we could have around 6 to 8 lights within an area of a 10-meter radius of the player. If we set the fade-out distance of those lights to 1,200, any more and we would get performance concerns. You could see how that wouldn't be ideal, because if you get more than 1,200 units away, the light will cull itself. But within the area of one module, we could get pretty accurate lighting. But we just recently switched to 5.5, upgraded to 5.5, and turned on megalights, and turn off the fade-out distance. So all the lights are visible all the time, and even with hardware ray tracing turned on, which is needed for megalights, we only saw a minor decrease in performance. We're still testing this and evaluating if the lighting is still as accurate using megalights, but so far it's looking really good, and we're quite happy. So when it comes to human spaceflight, managing limited space and translation paths is a challenge, especially in the Lunar Space Station, which has a much narrower interior than the International Space Station. In order to test translation paths and work areas, we have preset mannequins set up throughout Gateway that we can toggle on and off, doing various different tasks. We can also change the size of the mannequins on the fly from a 99% to a 50% to a 1% male or female, which means we're able to test the volume of the space with the largest and smallest possible body types. So all these things I've outlined in the previous slides are produced in service to the human-in-a-loop testing we provide the Gateway program. So during human-in-a-loop testing, we'll have astronauts with real space experience come in and perform a set of tasks. The astronauts will provide feedback on the difficulty of the tasks and any other factors we could not have foreseen without the experience of cohabitating in space with another human. One oversimplified example is having a galley table right next to the sleeping quarters. The galley table is kind of like the kitchen table, and it's like serves as a social hub for the astronauts at the end of the day. So you can imagine if you're trying to sleep, and then there's a bunch of astronauts literally like a foot outside your sleeping quarters, like just making a bunch of noise, that'd be annoying. Engineers don't necessarily think about these issues when they start designing equipment and layouts, but every astronaut we had in immediately noticed that this might be an issue. So an example of a run we might do is have astronaut move cargo from one module to another. The first thing I'll do is spawn some mannequins. There's one working on a science payload to the left, and there's one exercising to the right. And so this will be, the astronaut will be on the swivel chair in VR. It will be streamed on Teams. as well as recorded, and it'll just sort of stream of consciousness give us feedback, such as if there's enough space to maneuver without interfering with other crew. We'll do a variety of runs with different sized cargo and mannequins in different spots. So the Lunar Space Station project I just showed you is a fairly realistic simulation of a planned spacecraft. And there's a common assumption that realism always makes a simulation better, but that's not always true. In fact, trying to make things too realistic can sometimes get in the way of what really matters, which is usability, clarity, and insight. This is the balance our team constantly tries to navigate: fidelity versus usability. In some cases, we'll simplify geometry, exaggerate feedback, or remove detail, not because we can't add realism, but because it helps us focus in on the core design questions we're asking. The key is knowing when realism supports insight and when it distracts from it. It's not about building the most realistic simulation, it's about building the right one for the task at hand. So I'll quickly go through some more examples of projects we're working on now. One of the more recent projects I had the joy of working on was a lunar surface operations simulation. It's a multiplayer experience where players take on different roles, travel to different sites and collect mineral samples, all while managing resources like oxygen, suit power, and rover battery. A key goal of the project was to spark team discussion and evaluate how players work together to solve problems under pressure. At one point, the rover breaks down and the players must collaborate to fix it. Because the simulation was built for a specific customer, realism was not a top priority. My focus was on creating something easy and intuitive to play. For example, the lighting isn't true to the actual conditions of the lunar South Pole. Realistic visibility would have made gameplay much more difficult. I also simplified the tool belt. When a player drops a tool, it automatically snaps back to their tool belt. We didn't want players wasting time chasing essential equipment across the surface of the moon. So as part of this project, they also designed a spectator cam that shows the viewpoint of each player that we can run on a 5th computer, our 6th computer, our 7th computer, and record for future use. This has been integrated to our other projects and will display and export information depending on the customer's needs. I just recently upgraded it using the Common UI plugin, and the UI is much better now. We use a control rig and IK system to create the suit. When the player turns their head, it will slowly rotate the suit, sort of to simulate how if you're wearing a suit, that if you turn your head without turning your body, you're gonna be kind of looking at half the wall of your helmet. But of course, for a truly simulated suit, we would use trackers on the chest. But for the purposes of this project, the system requires no extra physical setup and provides enough visual feedback to give the player a sense of presence. So another example where Lumen lights and IES profiles came into play with our work is our work with the ground test unit, which is kind of like the generic lunar rover that they're going to use to build the actual lunar rover. So I worked with one of our engineers to place lights with specific light profiles, then brought her into VR to see if you could see them a set distance away. So through iteration, she was able to determine optimal placement and strength for the lights being used while keeping consideration for energy concerns, since there's a limit to how much power the rover is gonna have for lighting. We also had our designers in VR finding the correct placement and size of the edge key display. The edge key display is basically like the control panel for the rover. It's a display with a bunch of buttons on it. And so it was multiplayer, and we had the 2 designers sitting in the front seats and just an array of edge keys around them. And so they could pick up which ones they wanted and place them where they thought they should go on the rover. So while they're doing this, they're talking and making decisions on the fly and came to a conclusion pretty quickly. The team then used this information to procure materials, and it wound up on the physical vehicle. So when we design for spaceflight, we're designing for survival in extreme, unfamiliar environments. VR gives us a way to simulate those environments with a level of realism and interactivity that's quite powerful. Using Unreal Engine, we can quickly prototype and test scenarios, whether it's navigating through a space station, rehearsing emergency procedures, or evaluating lighting conditions in a lunar habitat. But to be truly effective, these simulations must go beyond physics and graphics. They need to reflect how humans think, feel, and perform under pressure. This is where human factors become so important. It guides us in shaping interfaces, layouts, and workflows that function in microgravity under time-critical operations or under heavy cognitive load. Because the truth is, a system can work perfectly on paper, but the second a human has to use it under duress, it can fall apart. VR gives us a chance to catch those issues early before we start to build hardware. So there's one more thing that VR brings to the table, something that, in my opinion, separates it from other mediums, and that's empathy. In VR, empathy isn't just an idea, it's real and embodied. It's emotional, it's physical. By simulating things like cognitive demands or limited mobility, we give designers, engineers, and astronauts a chance to step into those challenges long before launch. We're building perspective because when people can feel what it's going to be like out there, it changes how they design for it. Empathy turns simulation into real understanding, and when you combine that with the speed of game engine tech and the insights of human-centered design, we're building systems that truly support human beings in one of the harshest environments we've ever explored. This is how we're shaping the future of space exploration, one virtual mission at a time. I think I've talked enough for today, so if my colleague can pick it up.
Hi, thank you, Andrew. My name is Lee Bingham. I am an engineer at NASA's Johnson Space Center. I'm under the Software, Robotics, and Simulation Division of Engineering, and I'll be providing kind of a different perspective of using this very same immersive technology, but for training. So a few of the things that I like to cover: simulation and graphics, that's who we are, what we do. The use of immersive technology for training specifically. The importance for us of accuracy over artistry. And then kind of where we envision the future of training astronauts and crew using the Unreal Engine capability. So simulation and graphics, that's who we are. The ER7, or the Simulation and Graphics branch, which we're under, is responsible for the management, development, maintenance, and operation of numerous facilities that provide high fidelity, real-time graphical simulations. These are used to support both engineering analysis, mission planning, as well as flight crew training needs. So there are a number of tools across the agency used for simulation and visualization, but for us, these are our core capabilities that we use. First off, Trick. This is our simulation engine. It is the environment where we build our physics-based, 6 degrees of freedom, force torque, real-time simulations for space vehicle development. DUG, which is a dynamic onboard ubiquitous graphics. It is a NASA-developed OpenGL renderer used for training specifically for the International Space Station. Edge, which is essentially a wrapper around DUG, provides the added capability for interplanetary exploration. And then Dust, which is our digital lunar exploration site's Unreal simulation tool, is kind of our flagship desktop application built in Unreal Engine 5 that is being used for mission planning, as well as mobility and lunar landing simulation capability assessments. And then Inverse, which is NASA's virtual exploration rendered simulation environment, is a tool that we're currently developing and using that is being used to support current and future simulation and training needs. So the use of immersive technology for training. We typically categorize our training in kind of 2 ways. First, on the ground training. This is where we prepare and certify crew and astronauts for flight. So here in this example, we have astronaut Sunny Williams operating the mass handling robot in the virtual reality training lab. This allows her to operate a payload in microgravity with all the forces and inertias that she would experience operating a mass of certain payload. Once in flight, we have in-space training. So here we have astronaut Christina Koch using the simplified aid for EVA rescue, or SAFER, virtual reality trainer on board the ISS. Once they're in flight, crew will need to refresh training for various tasks. So we have part task trainers where crew will need to refresh themselves before they go out for an EVA or plan for any changes that have happened. So some of the considerations we put in mind for using and building an immersive training simulator. First off, what display environment? Are we using VR? Are we using AR? Is it a mixed reality sim? Do we need to use a dome or a video wall? What software are we using? Do we need it to be a physics-based simulation? Not always. And also, what graphics environment are we using? Hardware in the loop. So do we need specific hand controllers, crew displays, EDUs or engineering design units, or some fidelity of a mock-up? And then sometimes integration with robotics. Do we need a motion platform? Do we need mass handling or something like gravity offload? So here's a few examples of some of our immersive training simulators. The one on your left is our motion table simulator. Essentially, it is a human-rated Stewart table that allows a test subject or a crew person to operate and feel the forces and attitude of a vehicle, such as like a lunar rover or a lunar lander as they're operating it. The center image here is our visiting vehicle simulator. It includes a mock-up of the ISS cupola, as well as a hand controller and crew displays, and a robotic simulator that allows for crew to train for berthing and capture of a payload or cargo vehicle. And then the image on the right is our Orion docking simulator. This is in a dome projection system. It uses core flight software. It is using actual crew displays. It provides audio feedback for crew, as well as a physics-based simulation for crew to operate docking maneuvers for the Orion spacecraft. So I'd like to iterate for training the importance of accuracy over artistry. So it's important to provide an accurate representation of the environment in which crew will be working in. One example is the International Space Station. So the vehicle is always in flux. There's different configurations, different visiting vehicles, different things that are docked. Payloads will be changed, experiments will be relocated, robotics will be in different locations. So when crew prepare for an EVA, they need to know where all of these things are. So this is an example of our DUG tool. This is kind of essentially a reconfig of an EVA. So crew will go through this prior to exiting the vehicle. They'll know what handrails, every handrail has a specific label and serial number that they will traverse through, how long it should take between each station, where the tools are placed, which equipment and which payload they'll be operating with. So for planetary surface simulations, here are some key components that we use for modeling the accuracy. So first, terrain, where are we operating in? It's very data-driven. We look at imagery, we will look at statistical information, and we need to ensure that the 3D representation of this environment is accurate. Also, it needs to be geologically relevant. Lighting, also very important. For the areas of the lunar South Pole that we're exploring for the Artemis missions, lighting is very critical. So things like planetary body positioning, so the Earth, Moon, Sun system for the specific date and time that crew will be operating in, it's very important that the lighting and the position of those planetary bodies are accurate. Things like eye adaptation and camera modeling, so how the cones and rods of a person's eyes adapt to light, as well as cameras adapt to various lighting environments. So, cameras that work really well in bright environments don't necessarily work as well in lower light. And then, as Andrew mentioned, we use IES profiles that model physical lights, like the beam pattern, the color, and intensity of the lights themselves. And of course, importantly, validation. So, is what we're modeling correct? what are the limitations to our model in Sim, as well as what credibility do we have and where can this simulation be used. So we have lots of subject matter experts, SMEs, review all of our simulations. We have an accreditation standard for every one of our sims that we use, and we perform this for anything, especially when training crew. So this last part here is kind of where we envision, or I envision, training astronauts using the Unreal Engine system. So as you are all well aware, Unreal provides us kind of with a vast ecosystem of tools and resources suitable for space simulation and training. So we don't have to worry specifically of how a pixel is rendered. We can develop content and capability that provides us meaningful ways to train crew, inform engineering decisions, and plan for missions. Also, this is why Unreal Engine has kind of become mission essential for our work. First off, large world coordinates and double precision. Space exploration requires big numbers and precise numbers. Kind of photorealistic real-time rendering performance. If we have humans in the loop, it should be real-time, and it needs to be a environment that is representative of where they're operating. Virtual reality and multiplayer support. So being able to have crew or test subjects operate in a collaborative environment as well as an immersive environment. And along those lines with immersive, in-display has been also critical. This allows us to expand our capability to our pre-existing dome systems as well as our video walls. And again, just to reiterate, real-time performance is critical for human-in-the-loop training. So what we'll see here is kind of two different wireframes of our lunar terrain our rendering capability. One is on the top is our more novel clip mapping method, and at the bottom is a wireframe of a more traditional quad tree. Both are running real time on our hardware. As you can see, we can render the entire planetary system. And then kind of where we view the future capabilities in our development as well as things that are in our potential pipeline for simulations and training. First off, high-level architecture, HLA. This is an interoperability standard used for distributed simulation. So we envision that our graphics sim can operate as a active participant in a distributed simulation, in a federated real-time simulation. So this allows us to tie into disparate sims, but be able to provide an interoperability standard. So we want to build in our capability to take advantage of HLA. Robust real-time scene editing. Maybe this is used for USD, I don't know. But what we'd like to do is not require flight controllers and trainers to have to download the engine, an editor, clone our project, make edits to the scene and scene hierarchy, add models. We want to be able to give them an executable that allow them to make changes. So if they want to express a space vehicle in an inertial frame or a solar system barycenter or for a planet fixed frame, we want them to be able to do that in this executable, have it persist for future runs. And then finally here, something we're working towards is this web and cloud-based simulation delivery system. So we want to develop a platform that allows us to deliver live simulations through a web interface. So essentially, this is an example of our Dust application running on metal in a workstation in a laboratory. I've accessed this through a laptop that is not capable of running Unreal, but through a web browser, I can operate in real time and interact with all the features within this application. So the point of this is providing no install approach to access high fidelity simulations and visuals. So imagine kind of a Netflix for simulations and visualization capability where you can have a library of all your capability, subscribe to this, launch your application, join a session, and then operate your tool. So with that being said, I'll kind of wrap up with a short little minute-and-a-half video of kind of a lot of the really cool work that my team has kind of put together over the last few years using Unreal. And while I'm doing that, I'll just acknowledge this kind of front row folks here. This is our key team of developing this capability. So again, all this is running on commercial hardware you can pick off the shelf, all in Unreal, running real time interconnected with our physics-based simulations or with just the graphics themselves. So we're not just limited to planetary surface operations. We can do space vehicles, International Space Station. We're not constrained to just the moon. We can go to other planetary bodies. This video here is kind of a public outreach lunar rover simulation that our team has put together to kind of give an experience of how to drive and operate a lunar rover on the lunar environment. And then finally here, this is an accurate star field. This, I don't recall what observatory this is, but this tracks over time, and the observatory is tracking Mars. So, thank you. I just want to thank Andrew and thank Epic for allowing us this opportunity.